Morning all from the UK. How's everyone? Thank you for joining this third Surface Ventures webinar. So before we start, can I just check that everyone can really hear me on the mic? I think the best way to doing this is if you just can write in your chat box on the right hand side where you're joining us from today. Thank you. Great, thank you very much. That seems to be working. We've got a number of great places there. I hope the weather's nice where you are in the UK in Leeds. It's fairly miserable today, but oh well. So to begin, so my name's Tahid Khan. I'm a VP at Surface Venture, and I'm your host for today's webinar with Professor Ben Beek. So just to give a bit of background about Ben, after postdocs studies at Hull, Nottingham and UMIST, Ben joined the company Micromaterials, where he's been a director of materials research since 2006. He's got quite a large range of publications, ranging over 140 papers. He's a fellow of the Institute of Materials, Mining and Minerals, IOM3, a past chairman of the Institute of Physics Tribology Group, and is currently a visiting professor at a number of universities, Manchester Metropolitan University, Leeds and Huddersfield. So just go through the agenda today. So the plan is we're going to start with Ben's presentation, and then we'll come back to Ben after his presentation is complete, and we can take some questions. We're planning for the session to be around 60 minutes in total today. So think of it as a keynote speaker on your screen every month, essentially. So before we move on, let me just say a few words about Surface Ventures. We're a non-for-profit organization, and our mission is essentially to provide world-class surface engineering education for academia and industry. So every month, we aim to bring you a sector-leading speaker to present the current challenges and future trends in surface engineering, something like what we're doing today. So before we start, what we like to do in most of our sessions is do a quick poll. So today's poll is slightly different to the previous two. We'd like to learn a little bit about yourselves and our audience. So like last time, can you please answer the question that should pop up on your screen right now? The question is, are you working on high temperature material applications? Okay, brilliant. We've got a nice spread there. We've got 70% yes, and the rest no, but it's of interest. So that's great. So so the next steps is, so what I'd like to do is essentially hand over to our today's speaker, Professor Ben Beek. So over to you, Ben.
Introduction. I will just share my screen. Just bear with me. So I'm just waiting for the there we go. I think we're there now. Okay, everybody. So welcome to this part of the webinar where I'm going to be discussing the challenges involved in high temperature nanomechanics. So I'll start off by describing why we might be interested in high temperature nanomechanical testing, And that splits really between very much applications-driven testing, where we really need to know the high temperature hardness of materials for applications, and also fundamental studies of the temperature dependence of materials properties, and we can look particularly at things like ductility in materials that might be brittle at room temperature, for example. Then for the body of the talk, I'm going to be looking at how we can perform reliable high temperature nanomechanical tests. What are the main challenges we need to meet to achieve those things? And these really focus into three main areas. Firstly, we need to achieve thermal stability, so we minimize thermal drift in the tests. Then we need to control the environment to account for the fact that our material mechanical properties and chemical properties of the indenters and the test samples may change at high temperature through things like reactions and oxidation effects. And also, finally, we need to look about clever design of our experiments, both in how we set up the test load history and also how we analyze the results. I'm going to be going through that with a range of different examples showing how we meet those challenges in argon to 750 degrees C as a maximum temperature, and then in high vacuum up to about 1,000 degrees. And then I'll finish off with a few future research directions where the research is currently going. Okay, so in coating research, we typically, there's been a big trend to try and produce coatings that are as hard as possible. And this is shown schematically in this slide from Sam Zhang. And then there's been a bit of a pushback from that, realizing that actually in many applications, what is really required is a combination of hardness and toughness, because things that are very hard may be too brittle for the application. So this is a schematic, as I said, and really though, if you think of many of these applications of these hard ceramic coatings that Sam is thinking about, really this is only going part of the solution. Really what we need in these applications is a combination of high temperature hardness and high temperature toughness, and that achieves longer life of the coated systems. So a lot of our research revolves around evaluating materials for these extreme conditions. So if we think about one particular high temperature application, that is high speed metal cutting, and friction is generated during the high speed cutting. So the question might be, how high, what sort of temperatures do you reach? And if you do a continuous turning operation on a carbon steel, as in this piece of work here, thermal image from Linköping, you can see that you actually achieve very high temperatures around 900 degrees right near the cutting edge in this example. If you have a discontinuous cutting operation, in this case milling of a titanium 6-4 alloy, then you can see the temperatures are rather lower, but you still they're nevertheless very much higher than room temperature testing. So if we're trying to optimize coating performance for a longer life in these operations, in these type cutting tests, the question might be, how relevant are room temperature tests? And it's generally assumed that if a coating is hard at room temperature, it stays harder. It stays harder than another coating at high temperatures. And if you look at the little graph on the right, you can see for 3 different commercial coatings that actually this isn't always true. So the red coating is particularly okay. It's about 20 gigapascals hardness at room temperature, but you can see its thermal stability drops off much more rapidly than the other 2 coatings. So this coating is a much less effective coating, has to be swapped out much more often, reduces productivity in these cutting tests. It's been superseded, the red coating has been superseded largely by the other 2 coatings in some of these applications. And I should also say that in all the graphs that follow, when I put temperature on the x-axis, this really means test temperature. This is not the question of heating the sample up and then cooling it back down and remeasuring after an annealing temperature. This is the temperature we do the test at. So this is a good example here that typically you anneal things to make them harder, but actually when you test them at temperature, the hardness still typically drops. So as well as these temperature type of test where you really need to know the high temperature hardness, there's a wealth of other information you can get out of these nanomechanical tests when you have reliable data. So you can get, for example, position sensitive local mechanical property data in different phases. In the example in the middle of the image slide here, you can see a cemented carbide, cobalt with tungsten carbide grains in the cobalt matrix, and you can see a little indent in there in a carbide grain, and I'll show later how you can use these type of tests to get very, very sensitive information about the mechanical properties at high temperature of the individual phases and show how those build up to give you the bulk scale performance that you get. You can also look at time-dependent deformation and look at things like strain rate sensitivity, creep behavior, and how this is affected by the changing plastic deformation mechanisms in your materials, and that may also affect the amount of pile-up that occurs around the indentation. And you can also look at the ductility of small-scale structures and materials, particularly that are brittle at room temperature. So you can look at machined pillars, you can look at machined micro cantilevers, and I'll talk a little bit about that later on. So the examples here are showing silicon cantilevers and silicon pillars, and also a tungsten alloy. So to achieve this very high level of reliable data, you really need to think about three things. Firstly, things around instrumentational stability. So the heat, you have to manage the heat flows in the contact that generated by the high temperature test. So make sure that this heat does not generate to reach your measurement electronics and give you some sort of control unit drift for that reason. But equally important, and perhaps more important, is that you need to actually control the temperature in the contact to ensure that the probe and the sample are in a thermal equilibrium, so that when you do an indentation test, that you don't get heat flow as your dominant thing that you measure, so that you actually then measure the deformation of the material and not the thermal drift of the contact. The next set of things you need to worry about are around the changing chemical and mechanical properties of the indenter and sample. So if you think about the hard indenter material itself, which typically is diamond at room temperature, well, diamond works really well at high temperature testing up to about 450, maybe 500 degrees, and then it oxidizes in air, and that puts a pretty hard limit on using diamond above those temperatures. It just effectively burns away. You also need to think about chemical reactions between the tip and the sample at high temperatures that may not occur at room temperature, and you need to bear that in mind with your indenter choice. You need to also think about the hardness of the and even potentially the fracture toughness of the indenter material. So again, this may be very different to what it is at room temperature. And also you need to make sure that the indenter remains well bonded to into its holder at high temperature. So you may need to use things such as a very high temperature braze or a glass ceramic bond, as we've done at Micromaterials. And also, as I mentioned, the test samples themselves may also oxidize, and that also impinges on whether you can get away with an argon purge or whether you need to move towards high vacuum. And the final thing that we really need to consider is that in high temperature tests, typically we can get a lot more time-dependent deformation, or viscoelastic and viscoplastic deformation, and how we cope with that in the test design and also the analysis methodology is quite important. I'll give examples of how we can mitigate this in our testing to achieve high quality creep data and also high quality elastic modulus data. So firstly, if we consider what might happen if we simply have a hot sample and we indent that hot sample, then we might get heat flow. So one of the things that people have looked at is they said, well, maybe it's okay just to have put the indenter in contact with the sample, leave it for a certain amount of time, and then it will reach a thermal equilibrium, then we can do the test. And some manufacturers have gone down this route, and it's over the years it's become progressively less popular as it's been realized that really it's ineffective, typically in a large majority of situations, particularly for conductive samples. And this thermal model is sort of indicating why, that you don't really approach a thermal equilibrium. You have this very steep temperature gradient, which can exist, particularly at higher temperatures. And this is an example here. And the way to avoid it is to actively heat both the tip and the sample, and to precisely make sure those two things are at exactly the same temperature. So in the micromaterials nanotest system, we achieve that by a combination of things. We have a horizontal loading configuration, which is particularly useful because it allows any heat rising upwards from convection not to reach the displacement measurement electronics. As I mentioned, we have separate active heating of the probe and the sample, and we've controlled particularly how we thermally match those, and indeed we have to handle the different thermal masses, we have a power lock on the indenter side and a PID loop on the sample side, and this stops two PID loops fighting against each other. And we can achieve essentially a very localized hot zone, so that if you can look at the image where that shroud is there, that localized hot zone sort of keeps in that area remains very hot, and the area outside it by the shielding and the stage design is essentially much cooler, and that's one of the tricks to these measurements. So if we look again schematically, if we put a thermocouple on the surface, we can see what the actual test temperature is. And in the example, we've done this in our lab. We've looked and we've done for a test we did at 750 degrees, and we can put another thermocouple at the back of the hot stage, and we can see that's about 3 degrees above room temperature, so that's almost exactly the same as room temperature. So this is very useful because that means that essentially we've really localized that hot zone, and that allows us, amongst other things, to put an SPM 3D nanopositioning stage, which gives us very fine scale positioning. And these things don't like being exposed to high temperatures, but they work quite happily, and they can integrate quite nicely with hot stages, and that gives us more power that we can do with our high temperature tests. So we need to be sure that we have minimal thermal drift in our tests. So if we look at an ISO 14577 type load history for an indentation test on a metallic material, we load up, we have a hold for creep, the idea being that the creep exhausts, and then we have a relatively rapid unload, and then we have a long period at 90% unloading where we are essentially measuring thermal drift. And what the ISO standard says is that we need to ignore the creep recovery part at the beginning of this and then take thermal drift from the last proportion, typically 60% of that data. So if we have more creep at high temperature, typically we may need to extend that thermal drift period longer. So this is an example of how it can work. And in these examples, and these are on a polycrystalline tungsten sample tested in high vacuum. And whilst you might think, well, if I'm getting a measurement, how do I really sure it's not creep recovery, and how is it really thermal drift? Well, you can set up tests under different conditions, and if you do that, you can be fairly confident that what you're seeing is actually minimal thermal drift. So if you look in this graphic here, in the first 20 seconds or so, we're getting a fairly quick depth change, and that's down to the creep recovery in the material. So we're seeing that is lower at lower temperature, and it also increases at the higher temperature. This is exactly what you expect from a materials effect. But if you look at the last part, you can see that's now independent of the last 60 seconds. That's independent of this loading history and actual test temperature. And that gives you a lot of confidence that the thermal drift is minimized in these conditions. So in these examples here, typically the drift's about 0.05 nanometers per second, which is not quite as good as room temperature, but it's certainly good enough to do high temperature tests. And a little picture in there from a high temperature system at Oxford University, and you can see there that the tip glows at high temperature. So you've got heating on both sides of that contact. So the next thing we need to worry, as I mentioned, is that we need to consider the stability of the indenter material itself. So diamond is a very popular choice, and it works very well for high temperature testing as well, provided that you keep the test temperature under about 450, 500 degrees. And this is an example in this case from Cambridge University, and that's an AFM image of a Berkovich indenter. And what we can see is that it looks just pretty much exactly the same as it did prior to a large amount of high temperature testing. This is another image. In this case, this indenter hasn't even been used for high temperature tests, but it has been exposed to argon atmosphere at 900 degrees for about an hour and a half. And you can see already you're getting some pitting in that material, and its area function effectively is going to change when you use high temperature tests, and it's going to make the test data a lot more problematic. So the other thing you need to worry about is that diamond itself isn't so effective at testing carbide formers such as steels, and this is again another image from Cambridge University, and what you can see there is that the top of the tip essentially has been burned away by contact with the steel sample. So we can say that essentially diamond is very good provided you can keep the temperature down, and that you really can't use it for testing carbide forming materials at high temperatures. So it is, as I say, quite a successful material. So this is an example using diamond as an indenter from Manchester University, and here they've tested a so-called Triso nuclear fuel pellet, and they've tested the silicon carbide layer in that material, and then they've looked at the effect of irradiating that to simulate what might happen in a nuclear reactor. And what you can see is that you can effectively get reasonable mechanical property data across that temperature range to 500, and you see a softening without any particular increase in data spread. So we also need to worry about not just the indenter but also the sample. So I particularly like this picture. This is from Frank Lofi, and it's in this case it's a cemented carbide insert, and this has just been exposed to an 800 degrees air environment, or possibly a pure oxygen environment, and you can see the little cutting tool insert, the sort of square insert with the rounded corners before testing, and rather dramatic in this case shape change that occurs due to this swelling and formation of this tungsten trioxide. So even though such extreme things don't necessarily happen in nanomechanical testing, it is still something that you need to worry about, and it's not really possible to test on once you get oxidation, because essentially then you're testing the oxide properties and not the properties of what is underneath. So one way around this is to test in an argon environment, and in this case this is a cubic boron nitride indenter. This is some work from Lund University in Sweden. And again, you can see quite happily that in this case the error bars are actually slightly better at high temperature than at room temperature. So you have no problems at all in this case. In this case, up to about 700, 725 is probably the limit for that application. So this combination of using a hard cubic boron nitride indenter and an argon purged gas environment is quite successful at testing a wide range of other materials as well. So here, for example, we can contrast the high temperature properties of a high strength alloy steel developed by Rolls-Royce and the standard D2 tool steel, and we can see, for example, the softening temperatures change and the error bars remain low throughout those temperature range. So we don't have the same problems with the CBN indenter and steel as we do when we're testing steel with diamond. So the CBN is the preferred choice for steel. We can also test hard coating systems. So this is some work from Virginia Tech, and in this example we're looking at silicon carbide, and in this case we're looking at during deposition, if we put nitrogen into that system, we get silicon carbonitrides, and we can see immediately that the red curve shows that these silicon carbonitrides are less thermally stable, less mechanically good properties at high temperatures compared to the amorphous silicon carbide. So then on the little graphic on the left, you can see an example of one of the instruments sitting in an environmental chamber. So again, another example in this case where this combination of the nanotest with cubic boron nitride indenter and argon purging has been used to look at the mechanical properties versus temperature for two different types of cutting tool material, in this case where they differ from having an alpha and a kappa alumina top layer. And you can see in this example here that the alpha alumina remains harder throughout the temperature range. And there's a little bit of variability in some of the data, but it typically remains pretty good, and this is quite useful in explaining the tool life data. So hardness is important, as I say, for tool life data, but actually in many tribological applications, these composite parameters such as the hardness to modulus ratio which is a measure of the elastic strain to break, and this h cubed over e squared parameter, which is essentially related to the resistance to plastic deformation, can be particularly useful in predictors of tribological performance. And we can work out not necessarily very high values, but we can determine what are the optimum values of these things for different tool life in different applications. So for example, on the left there just shows a few different examples of PVD and CVD coating systems, and that shows, for example, the H/E ratio changing as a function of temperature. And in determining this, I probably should say a little bit out of order that in working this out, we need to account for the changing elastic properties of the indenter as well, which changes very slightly. The CBN indenter changes very slightly over that temperature range. And we can also see on the right that the parameter h cubed over e squared, its temperature dependency is much stronger than the h/e. So when we're using room temperature, we're saying, well, it correlates with tool life. Actually, what we really need to be doing largely is looking at the high temperature behavior, and it's quite different at high temperature for this. And what we can see in this case is that a multi-layer nanolaminate titanium aluminium silicon nitride system, which is the brown curve there, really has the best performance at high temperature, and this actually fits with its high temperature tribological data in many applications. So we test these materials with CBN, and this has been fine typically over the years, but as coating designers have got better, then actually we're worrying a little bit about the wear of the CBN indenter. So what we're seeing particularly we're asking that question, is the indenter hard enough at high temperature? So diamond, typically its hardness drops, but not too much. Other materials, typically they have lower hardness, and then the hardness drops typically as the temperature increases. And this can become a potential issue if, as I say, if we're testing hard coatings that remain appreciable hardness with appreciable hardness at high temperature. So with this in mind, there has been a real search for different high temperature indenter materials, and some of the things that people have looked at, for example, are cemented carbides. And this slide, again, another slide. Thank you very much to Jeff Wheeler from ETHZ for supplying this. And again, these are data taken from non-depth sensing techniques. So these are bulk hardness tests on large samples of bulk material. So these are not possible to get these tests on at these necessarily these extremely high temperatures over 1200 yet with nano indentation, but these are bulk hardness tests. And you can see in there, for example, which of these carbides might be useful for further exploring. So boron carbide is particularly promising, but there's not much of it about, so we're looking at other materials. So up until now, I've been talking about controlling, basically eliminating almost all the oxygen with an argon purge. This is particularly effective in most cases, and if we want to test over 500, we combine it with testing with CBN indenters. For some materials, particularly superalloys, we use sapphire indenters instead to avoid chemical reaction, and it's a particularly effective solution in most cases. But in some cases, we need to go towards high vacuum, because we really need to have no oxygen there at all. And this is an example on the right showing a nanotest extreme. The inside of one, you can see the design's a little bit different to allow for this high temperature testing in vacuum. And this really can negate any sample and indenter oxidation issues. So one particular application of this, and it's particularly timely now, since Tuesday the construction started on the ITER fusion reactor in south of France, and tungsten has been used in these as a plasma facing material. And in this application, the tungsten components are subjected to irradiation damage, and a lot of research is based around trying to simulate that type of damage, but with ion beams. And in this case, the samples are not radioactive. The damage is restricted to a few microns within the surface, and we can test these in nano indenters. So they're really it's a good way to simulate the radiation damage that is caused by alpha particles and fast neutrons. So the problem is, though, that if we're trying to test in argon, the tungsten sample is essentially, the oxidation is too fast, and you get this formation of this thick tungsten trioxide layer, as we can see. So at room temperature is not a problem, because there's a native oxide, but it's very, very thin, and essentially we don't see that in the indentation data. But at high temperature it's really thick and porous, and it's not possible, certainly not possible, to test any irradiation effects. So the solution is to test in high vacuum, as this is an example of the surface structure on a polycrystalline tungsten sample, and you can see the surface structure is retained after the tests. So the next thing that we need to worry about essentially is the enhanced time-dependent deformation that we see at high temperatures. So this, again, is an example on a polycrystalline tungsten sample. So these are data taken in high vacuum. And in the temperature range 750 degrees to 950 degrees, actually what's interesting is that this material doesn't particularly soften over that temperature range. So the loading curves, you can see, are almost superimposed. But actually what we do see is we see greatly enhanced creep in the whole period at high load, at peak load. And we need to take into account of that if we want to get accurate elastic modulus measurements from the unloading curve. And the various strategies to do that involve increasing the hold time at peak load, unloading more quickly, or using a viscoelastic or another analytical analysis. So this is reminded me of another example. In this case, this is a G18, which is a glass ceramic seal material, and this in a solid oxide fuel cell. And in this material is quite creep resistant up to about 550 degrees, but up to above 550 degrees, it's really susceptible to high rates of creep. So I illustrated that there for the red curve, and you can see that high rate of creep is retained at the end of the loading period. So you can imagine that creeping rate is continuing as you unload, and as it's up, and then therefore it's affecting the contact stiffness. And this is a headache for nanoindentation data, and we need to handle this either analytically or essentially get around that if we want to get accurate elastic modulus measurements. So one of the things that we've done, for example, is taken a correction, a viscoelastic correction originally designed by Alfonso Nagán for room temperature tests. And as it's shown mathematically there in terms of compliance, not stiffness. And what we can see is that that type of correction allows us to effectively correct from the unloading stiffness that we see with this anelastic deformation occurring within it, to get back to what the real correction would be without that anelastic or viscoelastic deformation here. So here's some data back from 2008 on in this case CMSX4, which is a popular nickel-based superalloy, and we can see there that again its hardness doesn't particularly drop at high temperature, so the loading curves almost superimpose completely. And what we see is that if we look at the blue unloading curve, that apparently it stiffens up at high temperature, but in fact this is an artifact due to this anelastic deformation. It's not a bow that you see, but it's a slight stiffening up. And if you analytically allow for that, then actually you get data showing that in this case that the elastic modulus drops from 126 to 113 GPa, which is exactly what the literature said it would do. So these tests were done with diamond, which was possible because it was under this 500 degree limit. So obviously the applications of these nickel-based superalloys and the bond coats in jet engines are far higher than this. So it's nice to be able to test at higher temperatures, and for that you need to go to vacuum, and you need to use, in this case, sapphire indenters, because as I say, the cubic bore nitride indenters react with these samples, and they effectively blunt the tip, changing the area function too quickly. But sapphire indenters work well, and this is some work from Aachen, and thank you very much to Sandra Korte for supplying this slide. And what we can see again, this is the bond coat, the M. Crowley bond coat between the thermal barrier coating and the superalloy substrate. And this is just looking at the creep that occurs in 30 seconds, and we can see at 500 degrees, actually, it's very creep resistant. Actually, the creeps, if anything, slightly less than at room temperature. But then at higher temperatures, you can see a very high creep, and this is limits in its application temperature. And if you look at creep analysis and you look at stress exponents from that, you can see the little stars correlate quite nicely with what you see from macroscale tests. So also at Aachen, they've extended this work, and they've used their Nanotest Extreme to do tests in high vacuum with a sapphire indenter on both the bond coat and also the superalloy substrate. And we can see there that the mechanical properties are reasonably similar. Actually, the superalloy substrate softens less quickly typically than the bond coat, but nevertheless, it's quite consistent data. And that's the first time that in the world that we've been able to use nanoindentation to reach 1,000 degrees and get highly quantitative data throughout that temperature range. So they should be applauded for that. So as we go to higher temperatures, the critical issues, provided we have a stable system, and in Nanotest Extreme, we have a particularly thermally stable system, we don't really need to worry about thermal drift particularly, then the remaining critical issues are really material dependent. So these split typically into potential problems with indenter wear for hard coatings, and metallic alloy systems, typically we need to, say, doing under high vacuum to eliminate oxidation. We need to consider various different tip sample reactions that may be more likely at higher temperature, and we need to account for this higher level of time dependency and plan our indentation tests and the analysis accordingly. And over the years, we've built up a database of experience in how we design our type of tests. And going forward, I think there's going to be increasing use of certified high temperature reference materials with known elastic properties at high temperatures. And we can use these particularly in our high temperature campaigns, and particularly we can test them to provide a indirect verification of the tip shape area function at high temperature to check we have no wear, and this then gives an extra data assurance of the high temperature results. And lastly, we can look at doing some clever things with high temperature nanopositioning to target specific features in the material. So before I talk about that, I just thought I'd show this again, schematic. Thank you very much to Jeff for this one. And it's quite an informative graphic, because it shows essentially the increasing temperature, peak temperature with time. And what we can see typically is that the up until about 2010, the maximum temperature in these studies was around 500 degrees, because that was because diamond was used as the indenter. But then around then, just after that, we introduced CBN indenters that allowed people to reach higher temperatures up to about 750 degrees or so, 800 degrees. And then since then, we're able to achieve 950 and 1,000 degrees with the testing in high vacuum. So in this case, the plus symbols are the Nanotest Extreme and Vantage systems. So I showed you the schematic earlier, and I mentioned the possibility to put a nanopositioning stage, to mount the hot stage on a nanopositioning stage. So many of the systems that we have this configuration, and this allows us to use that nanopositioning stage to very accurately target our indentations or other type of nanomechanical tests that we like to do. So this is an example in this case from a National Physical Laboratory here in the UK, and here they've used this high temperature nanopositioning to precisely indent in specific grains in this multi-phase material. In this case, it's a cemented carbide, tungsten carbide cobalt material with a mix of basal grains and two different prismatic orientation grains. And what we can see essentially is that all of those properties change differently as a function of temperature. So we have the ability to get the temperature sensitivity of the individual phases in the material now. And Again, they've used, for convenience, they've used diamond at the lower temperatures, and then above 400 degrees, you can see it seamlessly switches, and they switch quite happily to use a CBN indenter. So another type of thing you can do is pillar testing, but also you can do micro cantilever bend testing. So this is some work, again, in this case from Oxford University. And here we have a focused iron beam milled array of micro cantilevers, and we image over the top of one of those cantilevers using the using essentially the tip as the stylus in the SPM experiment. And we can use that image and then use that to very precisely target where we want to do our bending test. And then that's very important, because then that goes into the maths to determine things such as the yield stress and modulus of temperature. And we can also look at things like the differences in ductility and increasing temperature. So we get very nice images. So that's actually effectively a high temperature SPM image, if you like, with the integrated nanopositioner taken at 700 degrees on a micro cantilever machined in silicon surface. And what we do, and when at Oxford University, when they've done these type of tests, they were able to pull out differences in elasticity, but also differences in ductility. So the red curve shows a typical example of a fully elastic, linear elastic behavior, bending, and then suddenly a fracture at very low temperature. And at high temperature, above this brittle ductile transition, then we get a much more ductile behavior before it fails. And indeed, you can actually see slip lines in tests at high temperature stopping before fracture, as shown on the right. Another more recent example from the University of Oxford, in this case, Bo-Xuan Lee and Dave Armstrong have been looking at multi-cycle tests, and they've been looking at these multi-cycle tests as a way to pull out fracture toughness tests, in this case on machined micro cantilevers of tungsten with 1% tantalum in there, and they're using, if you see on the right, be able to quite nicely pull out differences in fracture toughness that relate to the the onset of this brittle ductile transition temperature. So to summarize, I hope I've given you some examples of showing how important it is to be able to do these tests at high temperatures, and how it can really provide much more relevant characterization of the mechanical properties of materials for these when they need to operate in extreme high temperature environments. So reliable data is possible with care. You need to take into account minimizing or avoiding thermal drift by accurate temperature matching, active control of the tip and sample heating to get a constant temperature in that contact zone, so-called isothermal contact. We need to avoid indenter sample reactions and indenter sample oxidation by accurate accurate environmental control. We need to consider indenter blunting, and we also need to account for any time-dependent deformation in terms of how we set up the test and how we do the analysis to mitigate this. As it's not just hardness and elastic modulus, as I said, you get a wealth of other information from all the other different mechanical tests you can do now at high temperature. And these results really are helping us to improve our understanding of the links between the microstructure and mechanical properties of performance of materials in these environments. So nanomechanical properties at 1,000 degrees or higher are now perfectly possible. And to reach high temperatures, one of the main challenges is certainly to develop indenter materials of enhanced durability. So that's a key area of research. And I'd just like to finish by acknowledging my colleagues and other collaborators, and thank you very much to the guys on the left for supplying these some of the slides as well. And also, for further reading, if you see on the right, the publication at the top is a short review which describes many of the studies that I've talked about in this presentation. The one in the middle is the first example of reaching 1,000 degrees, a very interesting article again by Arken. And a little bit further ago, Jeff Wheeler and Hannes Mikler's paper on indenter materials is also well worth a read. Okay, thank you very much.
Great. Thank you very much, Ben. Interesting presentation. So what we're doing is on the chat, we're releasing a few of Micromaterials brochures, which may be of help and add more to this presentation, maybe of interest for yourselves. So it's on the right-hand side. There's a tab called Handouts, so feel free to download that. What I'm going to begin to do is there's a few questions coming out, so I'm going to read a few questions out, and there's a few comments too. So let's begin. With Peter made a general comment. The use of argon atmospheres for hot hardness testing has been known and practiced for many decades. It's given a reference. It's also been in use of has been in the use of CBN indenters also. So that was just a general comment. Thank you for that, Peter. Thomas, dear Ben, excellent work and presentation. Perhaps you can help me. Oh, sorry, just lost my chat. Sorry, just bear with me 1 second. What type of hardware coatings can you recommend for aluminium-based alloy working in corrosion atmosphere? Aluminium structure works as a construction bar on which another element moves, but the aluminium bar has corroded hardly, and I am looking for a hard coating that will protect the material against such corrosion process.
Well, that's a very much a materials rather than application high temperature type question. But what I would say is, if you just had a thin PVD coating, then I think it wouldn't necessarily give the same level of load support. So I think you're going to need something more like a duplex type solution to that, where you have a gradation of a hard layer and a sort of corrosion resistant layer. So there are a few options for corrosion resistant aluminium, but you need potentially to put down multi-layer type system or a duplex system that minimizes also, if you have these multi-layers, then potentially you can avoid these weak columnar boundaries that might form ways for the corrosion to get into the underlying. So you need to structure potentially the coating system to allow for that.
Brilliant. So I'll move on to the next question by Ali. Hi Ben, in development of friction materials, what kind of challenges are we expecting using nano indentation to analyze the mechanical behavior of carbon-based materials such as graphene?
Well, that's a very good question. Certainly, so graphene itself is a very delicate material, essentially. So we've certainly done high temperature tests on things like diamond-like carbons, which potentially are much harder, because these have applications in high temperature in automotive engines and things like that, up to about 300, 350 degrees, something like that. But the graphene itself is, and other type materials like that, they're much more delicate. So the challenges are based around the fact that they're very thin. So therefore the indentation response essentially is a composite of the graphene and potentially what the layers underneath. So it's potentially an idea then to put those graphene layers down on, again, a strongly load supporting substrate.
Great. Next question. Alina, hi Professor Ben, thank you for your presentation. Just wondering if the surface roughness has an effect on the accuracy of the measurement. How does it affect the performance of the indenter?
Yes, I think that's an astute question, certainly. So roughness certainly can have an effect. In some cases, people polish coatings after deposition prior to testing. You have to be a little bit careful in doing that you don't introduce surface stresses that actually modify the properties of the coating. So certainly one of the things to look at for these systems, if you want high quality data, is to really get good substrate surface finish prior to deposition. I would say that's one of the key things. In terms of the data, then I think as I say, roughness can have some effect, so therefore it's a question of it can be more beneficial to do large arrays of indentations and take a sort of statistical average of that, and then it effectively knocks out that effect of roughness from the data.
Brilliant.
Yeah.
Another question by Wan. Thank you very much, Ben. Please advise if the method can be used for worn coated surfaces. Basically, the coating has been damaged somehow.
Well, I think so. I think we could probably in future look at things like tribofilms and things like that, because we've got this positions with this nanopositioning stage that we can use. We could potentially look either at high temperature or subsequently back at room temperature, and we can accurately position on the different phases or the worn areas or something. So again, it's almost a combination effort of doing enough measurements to be confident that you don't have artifacts due to things like roughness or lack of load support in the worn area or something like that. So it's statistical. You need enough data, basically.
Brilliant. A few more questions. We have Fabian who asks, what could generally make a material hard and tough?
That's a good question. So, what can generally make a material hard and tough? So people have looked at things like nanolaminates for a coating system are quite interesting. So you have essentially a system where cracks might occur, but they're deflected by a range of different interfaces. So you have a range of different mechanisms there where you get micro cracking mechanisms and other small scale plastic deformation mechanisms in that structure that avoid large scale build-up of stresses and stress accumulation that can drive large-scale fracturing systems. So a lot of coating design is based around this compromise between putting some sort of phase in there that might be more ductile, or structure in there that might aid crack deflection. But it's certainly a challenge, because you can't put too much in, because otherwise the material loses hardness.
Of course, great answer. Sufyan, is H/E and H3/E2 only used to characterize the coating, or can it be used to characterize the material properties such as 3D printed alloys?
They're certainly useful with indices, particularly H/E, because it relates to elastic recovery as well in indentation. So it's quite a useful thing in terms of phase mapping and things like that. It's been shown to be highly effective in terms of determining if you're multi-phase material, different crystals and things like that. But it can be almost thought of as a sort of parameter that encapsulates the ratio between how plastic something is and how elastic something is. So we found, particularly for coated systems, that it shouldn't necessarily in all applications be maximized, but there may be an optimum value for different applications.
Great. Jilling, how is the contact compliance defined?
The contact, yeah, that's a good question. The contact compliance, I skipped over it, but it's just simply 1 over the contact stiffness. So they had that equation there, that Fagnigan, because mathematically it's easier to show the relationship with this unloading stiffness, but by turning it over to contact compliance. So it's essentially exactly 1 over the contact stiffness. That is the normal thing that goes into the elastic Oliver and Farr analysis that determines hardness and modulus.
Just bear with me. And Jilling's just a follow-up question. Will the contact compliance be affected by the shape of the indenter?
Yeah, it's a good question. Off the top of my head, I would say yes, in the sense that the shape of the indenter is what's resulted in that reaching that indentation depth and the amount of elastic recovery. So in that sense, yes.
Okay. Brilliant. Thomas, can we use your concept for better performance of thermal barrier coatings like YSZ, Deuteria, Stabilizer, Zirconia?
Yeah, I didn't include him on that, but certainly we have also been successful at looking at these type of TVCs at a high temperature and looking at the effect of thermal aging, for example, on these things. And what we've seen is that although you may thermally agent a TVC to increase its hardness when you test it at high temperature, actually the hardness of a TVC is also much lower at 1,000 degrees. So at 1,000 degrees, it's I think something like 1 or 2 GPa. So it's nothing like the sort of 8 GPa that you might expect at room temperature.
Brilliant. And I think we'll take this as a final question from Peter. Sorry, just bear with me. It's just edited question. Why do you get big differences between macro hardness and nano hardness for many alloys? Example, cobalt, chromium, molybdenum alloys.
I think you get so-called indentation size effects, and these things typically are there due to strain gradients and things like that. So there's theories of strain gradient plasticity that used to affect these things. And typically you get a higher hardness, and it's to do with the different amount of dislocations that you may access in these different types of tests, and the geometry of the indentation test at these small scales.
Brilliant. Right, I'll take one final question. It's from sorry, just bear with me. Feng Zai. Many thanks, Ben and host. In order to minimize the effect of thermal drift, a faster unloading rate may be considered in general. Can you please provide some comments on this?
Yes, because the thermal drift is happening over any length of time. So essentially, if you drop the unloading, if you increase the unloading rate by a factor of maybe 2 to 5 or something compared to the loading rate, then there's much less time for that thermal, that time-dependent deformation to occur anyway. So I say there are different ways to analytically determine it with this Feng-Nagin correction. I also didn't mention, but it's another thing I would recommend people look at is the Oliver and Farfer coatings approach from SIO company. That's another particularly interesting analytical way to deal with this time-dependent deformation in unloading, get accurate elastic modulus measurements.
Perfect.
So it's a combination of 3 things. It's experimental analysis. Yeah.
Brilliant. Right, I think on that point, we'll begin to wrap up. If you do have any questions, you can feel free to email Ben. That's all right, Ben?
Absolutely. Yeah.
Perfect. So if you do have any follow-up questions, I do appreciate we may not have answered every single question out there. We do our best. So just want to say thank you for all the questions. Again, just want to thank Ben for this really engaging talk. Thank you for sharing. Really appreciated. Thank you to Micromaterials for supporting this webinar. As a reminder, you will receive a link for this recorded video automatically from the host, Demio. Our aim is to organize the next webinar towards the end of September, so stay tuned. I'm sure we've got something really exciting for yourselves again. So hopefully on that note, we'll see you next time. But for now, thank you for joining today, and have a great day and the rest of the week. Thank you, everyone. Thank you, Ben. Bye.
Thanks, Larry, as well, for your moderating.
Thank you. Bye.